Welcome to the lecture number 72. So, we have been discussing about the aerodynamic force and moment acting on the satellite if it is spinning. So, the last time we worked out the force acting on the satellite once it is spinning, and in this class we will finish the torque acting on the satellite once it is spinning due to the atmospheric drag. Okay, so, the torque acting m arrow, we already I have written here once the satellite is spinning. So, m arrow will be written as r cross df arrow. So, this is the basic equation where r is the distance of the point of the elemental area from the center of mass of the satellite. So, we need to insert all those values what we have written earlier. So, this can be written as h cos alpha and df arrow we have to insert. So, if we write those values, so this is V c r times V c r dot d a minus V c r times omega dot r cross d a Okay, so, we divide into 3 integrals. So, we can write this as cos h cos alpha r cross, here this part we can reduce it to V c r square V c r cap, and this part we can write as d a cos alpha minus and obviously rho is missing. So, rho we will put here in this place, rho a, this is rho a. So, h cos alpha as I have told you that we have to be very particular about where the cross and dot products are lying, and we have to follow that sequence. Any change in that sequence will produce wrong result. Similarly, from here also we can take it out the V c r. Okay, so, rho a times V c r h cos alpha we are picking up here, and here the part r cross we have missed out. So, this r cross is there, r cross we have already taken into account here in this place. So, this also must be taken care here in this place. So, that will appear as r cross V c r, because this part is a vector, this part is a vector, and together it makes a scalar. So, this cross product is going to operate only on a vector. Okay. Therefore, r cross V c r. Similarly, here we have this V c r, I have taken it outside, and then h cos alpha which comes for this particular one, okay, so h cos alpha, and then rho a also we have taken outside. This is omega r cross omega cross r, okay, and then V c r cap dot dA. Rho a times V C R square, this term can be taken outside, H cos alpha times R cross V C R cap times dA cos alpha. If you remember, this quantity is nothing but R square, we have written this as E double bar, okay, or in terms of inertia dyadic, if we write in terms of the identity matrix. So, this can be written like this, R tilde times R tilde transpose V C R cap dot d. It is little lengthy, but it is not that difficult. So, if you follow a systematic method of working out, so you can get into any kind of research, okay, because the research is a systematic method of doing the mathematics. Okay. Obviously, if the this area is more mathematical, that is why I am telling, and together with the physics is also involved, a lot of physics it is there. Okay. So, this V C R, this is not depending on the integration sign. So, therefore, this can be taken outside. So, in the next step we do this. H cos alpha times R times dA cos alpha, R cos alpha times dA, this is the first term, and then cross is there. So, the and cross is operating on V C R. Okay. So, V C R we will be putting here V C R cap, and then this cross is present here. Okay. So, you can see that the term which is present here this is nothing but your A p times C p. So, this way all the terms should emerge out. The second term then we are picking up minus rho a times V C R H cos alpha and this term is dA cos alpha. So, for this we put here dA cos alpha VCR square AP times CP cross, or if we put here in the matrix notation. So, the same thing can be written as CP tilde times VCR cap. Okay. So, this is the first term and minus rho A times VCR, the second one I am taking. So, here little bit of rearrangement is required. So, I will throw this okay. Let us name this. This is the first term, this is the second term, and this is the third term. Okay. So, let me bring the third term first here in this place, so that we shorten the process instead of copying the whole thing again and again. So, this is rho A times, this is the first term here, rho A times VCR, and then this quantity which is written here. So, this quantity we write as I A. This is the moment of inertia term. Okay. If we multiply it by mass, so you get a moment of inertia term. So, we are not integrating with respect to mass, but rather with the area. So, we get a equivalent of that. So, the second moment of area, basically this quantity becomes second moment of area. So, this we can write as I A times, and one part here is missing, somewhere we have omitted while writing this. And if you remember that once we write it like this, we have to also write here omega tilde for this part. This is r times r cross omega cross r. Okay. So, this will be this times omega, and because this quantity is scalar. So, writing it this way is not a problem. Okay. So, therefore, this can be written as omega tilde. So, this is your third term. So, now it has got shortened out, and the second term we can treat it. So, in the second term we require little bit of treatment, like this is a scalar. So, we can move it anywhere, okay, and we reverse the order of this and write it like this VCR cap. Okay. So, and cross sign can be taken outside, and this becomes R. So, this is H cos alpha first, and then for this the R will appear. Okay. So, what we have done, that R cross VCR, which we are writing a VCR cross R. So, for that a minus sign will appear. So, this minus minus that will make it plus. Okay. But again we are going to change it for what we will see here. We are going to put it in a particular order. Okay. So, this is R, and what appears here, this we can write as omega. We need to maintain a particular order for this. So, we will write this first as omega cross R and dot dA. Okay. So, this has been taken care of, this part is taken care of here in this place, H cos alpha is there. So, H cos alpha. Okay. we change the order of this. We write here as dA dot omega cross r, because it is a dot product. So, it does not matter. V C r cap rho a times V C r I a times omega tilde cross. Now, this quantity we have to treat properly. So, if we change the order of this, instead of writing it like this, if we write here r cross omega h cos alpha r dA dot r cross omega. V C r cap h cos alpha, this is r, and this quantity, then we can write this is basically dA tilde transpose. Okay, this is the area vector, elemental area vector. Okay. This is for dA dot. Okay, we have written here transpose, and then r. And this will be operating on omega tilde. So, we finally wind up this. So, if you see here, this is omega tilde is appearing here. So, we take out the related terms and write it in a simplified format. V C r A p times C p tilde cross V C r cap minus, from this place I is rho a V C r is taken outside. So, this becomes I a, and plus omega can be taken outside, here also this quantity goes. So, we are left with V C r cap cross, okay, and the quantity from this place to this place. So, this we define as J. So, V r cross J, and this will be operating on omega tilde, where J we are writing as h cos alpha times r tilde dA tilde transpose times r tilde cross. This is J, and I a we have written as h cos alpha cos alpha dA Okay, so, this is M aerodynamic. One bracket will be also here in this place. this is the inside bracket. So, if the aerodynamic torque is present, if your satellite is spinning. So, I will copy first this expression on the next page and then I will talk about this. So, what we have got m aero rho a times V C R and then V C R A P C P tilde cross times V C R cap minus I A plus so this term, or either say this whole term is appearing due to spinning of the satellite. Now, one thing we must be careful, while in the previous lecture also we have discussed, while we have written this equation. Okay. So, omega does not include atmospheric rotation, which we have already included in VCR, but omega is the angular velocity of the satellite with respect to the atmosphere. Okay, this part is important here. Omega is the angular velocity of the satellite with respect to the atmosphere, okay, and that will decide at what speed the particles are coming and striking the surface of the satellite. Okay. So, this part is your important part to mark. Okay. So, here omega tilde, this is the angular velocity of the satellite with respect to the atmosphere. However, this omega with respect to the atmosphere means this is with respect to the atmosphere. Okay. This can be approximated as omega inertial, okay, because it does not V, if you look into the quantity omega cross r, this quantity is much less than VCR, okay, magnitude wise. Okay. So, therefore, this assumption is safe. Okay, we can replace this omega atmosphere by omega inertial. So, if you do this, so then omega tilde here we can indicate this is equal to omega inertial of the satellite. So, it simplifies your expression then. Now, as we were discussing this is a part which is coming because of the angular velocity of the satellite with respect to the atmosphere, which we are telling that you can model as the omega inertial. So, if we look here in this expression very carefully, so it says that the aerodynamic torque, it depends on the angular velocity of the satellite with respect to the atmosphere also. Okay. Not only this part. Okay. So, this part will, so the rotation of the satellite, if the satellite is spinning, Okay. So, that spin will say the initially your omega here, this is omega 0 initial, omega initial, this is the right in the beginning. So, because of this it will start decaying, it will not stay at this value, and therefore, your spinning satellite will stop spinning after some time. It may be a long period, but ultimately it will come to a halt. Okay. And therefore, in any long range satellite attitude control problem, you need to take into account all these forces. Okay. If you are looking for the stability problem, so you are looking into the you are looking for a short period. Okay. The same thing is in the case of the aircraft also, the navigation problem and the control problem. So, control problem there or the stability problem, what we say for the aircraft, it is done over a short period of time, while the navigation it is done over a long period of time. So, there the curvature of the earth will be taken into account also. Okay. So, if the satellite is you are putting for 10 years in the orbit, okay, for 10 years you are planning the mission. So, you need to do all this analysis very meticulously, at least you have to do the simulation. Okay. Now, as far as the satellite attitude control is concerned, so rest of the things are as usual, that you have to write the equation in this format, and if you have the gravity gradient torque. So, write here m gravity gradient torque, then if you have the aerodynamic torque. So, you will write here m aerodynamic torque. If you have the solar radiation torque, so you will write here the solar radiation torque, and any other like the m due to the AD1. So, there are so many things that we can add. So, rest of the things briefly I will write in uploaded material. So, this also I am not going to discuss in details here, because this will follow the same procedure as we have done for the M aero. So, I will introduce this and then rest of the things will be uploaded as the written material. Okay. So, all disturbances whatever you can add here in this place, and this gives you the satellite attitude dynamics problem. Okay. Now, whichever is significant, like if you take m solar, so m solar radiation pressure, if you take at the geostationary height and at this height, so it will be almost constant, okay, because as compared to the distance of the earth from the sun, this distance is not very large. Okay. So, we will come to this problem later on. So, it does not matter much, but if you are looking for the aerodynamic, so aerodynamic torque is much higher here in this place, okay, as compared to the geostationary orbit. Here there is geostationary orbit. So, atmosphere is almost nil here in this place. Okay. So, you will not get the aerodynamic torque as here in this place as you are getting here. It is a very strong here in this case, okay, say at 300 kilometer altitude. Your satellite, if you do not correct its orbit, so it will be pulled down into the earth atmosphere because of the aerodynamic drag. So, similarly for the attitude also this gets affected because of the gravity gradient, aerodynamic torque and the solar radiation. So, thereafter whatever the procedure we have chosen to analyze the system, the same procedure can be chosen, and this can be accommodated along with the gravity gradient for the linearized system. Okay. So, we cannot do in so much details all these things here, okay, but the procedure remains same, and thereafter obviously the theoretical analysis involved. If not, you can look into the system behavior over a long period of time just by without the aerodynamic torque and solar radiation torque, and with the added aerodynamic torque and with the added solar radiation torque. Okay. So, a multi-stage simulation you can do, and then you can check that what is the effect over a long period of time. So, your what our conclusion is that the small torque due to the spinning m arrow is proportional to omega tilde here in this place. Okay. This is proportional to omega tilde. These quantities are constant, and therefore, this will make this omega tilde, and this is coming with a minus sign. So, this will make the system decay. Okay. It says angular speed will decay over a period of time. Okay, so, we will stop here, and in the next lecture I am going to discuss briefly about the solar radiation pressure, and in a very brief manner. So, we will continue in the next lecture. Thank you very much for listening.